So, short video companion to the notes that you've gotten here. Okay, dot products. Here's the definition. It's the product of the x coordinate, the x components, the horizontal components, added to the product of the y or vertical components, and you get a scalar, a number. So when we're taking the dot product of u times u and v, you just take the 3 times the negative 2 plus 5 times 7, add them up. Add up those products again. Product of the horizontals, product of the verticals, horizontals, verticals, add, ta-da. So how about 2v, the dot product of 2v and w? Well, what's the 2 times the horizontal for v times the horizontal w plus 2 times the vertical for v times w, the vertical for w. Add them up, as you can see down here, add them up. And as we go along, we can do that. Notice we get positives, we get zeros, we get negatives, and notice, okay, so we tried something different. Let's try t. So t dot t, so itself, the dot product of a vector at itself. So the horizontal is 2, vertical is 3, so the 2 horizontals are 2 and 2. 3 and 3 for the 2 vertical components. Well, we know that's 13, but notice that's 2 squared and 3 squared. Well, where else have we had 2 squared plus 3 squared? To square the horizontal component, square the vertical component. Oh yeah, if we took the square root, that was our magnitude of that. Well, if we take the dot product of times the dot product of the dot product of a vector in itself is the square of the magnitude. Now, might say whoop-de-doo, yeah, okay, but where that leads to is here, because if you think back to the law of cosines, we had the length of the two sides, the lengths of the sides squared. Well, the lengths of the sides, vectors in this case, is the magnitude. Well, the square of them is the dot product of the vector in itself. So that's where some of this is going to come into play. Here, we're not going to go through, it's actually explained in the book. You can go look at it. I'm not worried about it. Okay, so angle between the vectors. If we go the angles between u and v, here's the picture. Here's vector u, the 3, 5. Here's v, the 2, 7, negative 2, 7. And the angle between when they start, or sorry, when both of the initial points are at the origin. Okay? By the way, that is not the resultant. It's like I don't even think there's a name for it. It just doesn't work well. You'd have to move this v over here, and that then would be the resultant. We're not worried about that though. We're concerned like this here. Now, are there other options? Yeah. Right triangle options? Yeah. Use them if you want. But here's a quick formula for that. So the cosine of the angle between the cosine of that theta is the dot product of the two vectors divided by the product of the magnitudes. So here we go. We got the dot product from example 1, magnitude of u, magnitude of v. So if the cosine of that angle in between is dot product over square root of 34 times the square root of 53. And then, of course, to get theta, the angle, we take the inverse cosine of that value. Boom. That's it. Okay? So do the same thing between the two vectors v and r, the t and r, the two angle between. Well, what is the dot product? Magnitude of t, magnitude of r, formula, cosine of the angle between dot product over the magnitudes, product of the magnitudes, and turns out to be 180. Okay. Now, you'll find out that this value here, if you calculated it individually, then took the inverse cosine, that's -1. Cosine of what is -1 in degrees? Think about it. So 8, same thing. Dot product, magnitude of the two, set them up, plug it in. So dot product over the product of the magnitudes. And we punch it in and we get 90. Well, because of vectors, if the two vectors intersect in a right angle, we don't call them perpendicular, we call them orthogonal, because of the fact with vectors we have the possibility of the directions. Are they headed towards each other, away from each other, one toward, one away? So think about like at an intersection, how the different arrangements at that perpendicular set of streets, the different arrangements of the directions of the vehicles moving through that intersection. That's why there's a different name to it, okay? Orthogonal. Now, when we consider parallel vectors, 0 or 180, 0 degrees or 180 degrees, for the same reason. Because they're actually on parallel lines, but they could be headed the same direction or opposite directions. Okay? Quick recap of what that is. Quick recap of what we do with that. Okay, by the way, there is in here, the shortcut, if the dot product is 0. Right here, they're orthogonal immediately. You don't have to actually find the angle. But that's the only special case. All right?